Welcome everyone to Wave Analysis with Nortek Storm software. Our speaker today has worked at Nortek since 2001 and has focused mostly on the AWAC, specifically its AST and wave processing methods. Torsten holds a Master's of Science in Ocean Engineering from the University of Rhode Island and has authored numerous technical papers on wave measurements in various conditions from different platforms. Today, Torsten will discuss how to process and analyze wave data using Nortek Storm software. Ladies and gentlemen, Torsten Pedersen.
Thank you very much, John. So, what I am showing you here now is a Storm software. When you look at the window, you will see that it's composed of several different sub-windows, if you will. And down at the bottom you'll see that there are tabs, and this separates the sub-windows. So if I click this tab, it brings you to the current profile data, and if I bring you back to this tab, it brings up all the wave data, raw wave data. Since we're going to be only talking about waves today, I'm going to just focus on the wave data. So as I said a moment ago, we're composed of several smaller sub-windows, each which deals with a different type of the data collected during a wave measurement. So this lower window down here is more or less a history of the data that's collected throughout the deployment. So you see on the horizontal axis, you have the date and time of each of the measurements and the quantities values on the vertical axis. But now up here in this window, you have a single wave burst. So it'll show you a time series of the faster sample data. So here we have the pressure and AST data. Down here we have the velocity estimates from each one of the three beams. I'm going to enlarge the ones to the right-hand side, and what you see here is the processed spectra for this particular wave burst. So up here you see the energy density for both the acoustic surface tracking and the pressure, which is in green. And just below this, you have the directional spectra and the spreading spectra. Now below this window, you have what's called the full directional spectra. So this is a distribution of the energy over both direction, which is on the vertical axis, and frequency on the horizontal axis. Here it uses the AST to estimate this. So this is a combination of the directional estimate and the energy density spectra. Before I forget to point out, we have another tab over to the left-hand side, which is called Properties. And here what you have is information about how the instrument was configured and about the instrument itself. So if I click on Expand User Settings, you'll see that there's a lot of information about how the instrument was configured prior to deployment. And for head configuration, you can see that it indicates what type of sensors we have on board, as well as the instrument head frequency. And here you can see that this is a 600 kilohertz AWAC. So I'm going to click here and it'll go back to where it came from. So I'm going to return back down to this window down here. These measurements are taken in the current profile just before, in the current profile right before each wave burst. So it gives you an indication of what happens just prior to a wave burst. Right now what I'm showing you is the temperature and what's called excursive pressure. Now excursive pressure is a measure or an estimate based on the minimum pressure and the maximum pressure in the current profile. So it gives you an indication where a wave event might have happened. So you can see where we have peaks here is where we had wave energy. When it is flat, it's pretty sure that there's lower wave energy. So it gives you a rough approximation if you want to go ahead and search into the file. Now, each of these sub-windows has a grouping of buttons associated with it. Now, these grouping of buttons allow you to enable and disable viewing different data products. So this first grouping is associated with the lower left-hand corner. So right now I'm just showing excursive pressure and temperature as I showed you, but you might also want to look at, for instance, the tilt. So I pull this up, enlarge it, and you can see the blue and the red is the pitch and the roll, and the green is the heading. And you can see that this is more or less stable throughout the deployment, apart from a small event here where there is a slight heading change with the AWAC, which is probably a small movement in the frame during the deployment. But all in all, you can say that this is a well-deployed AWAC, which is one of the first things that I check when I look at wave data to make sure that the deployment was stable. Other data that's interesting to look at in this window is the pressure, which indicates the mean and max pressure that you might have during this. Now, often you'll have a tidal signature, but we don't see much here, if any. There's also the position. And the position is interesting because it shows you where the position of the measurements were made for the velocity cells, as well as where the acoustic surface tracking was positioned. If you had followed along with the AWAC presentation, you would see how these are adaptively positioned during the current profile. Over on the right-hand side, you have the size axis, so it indicates the size of the cell or the size of the acoustic surface tracking. I'm going to reduce this now and return up to the time series above. Now again, we have groupings for this data as well, and you'll see that you can turn on other buttons such as the amplitude for each beam. The amplitude is these three colors down here, and then the light blue is the quality for the acoustic surface tracking. I'll remove that now. Oops, I turned off the acoustic surface tracking when I wanted to turn off this. Looking closer at the data, you can also zoom in on the data. So if you wanted to look at a particular event, you can zoom in just as I'm doing here. I'm creating a window, and you can look at the finer detail associated with the time series of the estimates. If I right-click, I can undo the zoom. I can also zoom in just on the acoustic surface tracking if I will. Undo zoom is by right-clicking and selecting undo zoom. Up here, we have buttons where you can navigate through the data. You'll see here I have one that's select profile graph. I can enable and disable it. I'll enable it here. And if I go down to the wave header data, I can go anywhere in this file and select on data if I want to look at it more closely. These buttons up here allow us to navigate through the deployment. So if I select the next button here, I can step forward and look at each individual burst. Let's see here. Now, if I want to change the colors of some of these and change how the presentation looks, I can right-click. I can go into customization, and I get this dialog box, which allows me to change the presentation of many of these features. If I select style here, I can see that the pressure defaults in this hard to see green, so I'm going to select on pressure and select black, and it'll appear much better now. Let's see, make sure that I am not forgetting anything in this presentation of raw data. I'll step forward and look towards the processing of data. Now for the processing data, we want to go into the processing settings. So I select processing settings, and the dialog box pops up, and it gives you the options for configuring the processing of the current data quality control and wave parameters. So I'm just going to describe what's in this so you have an idea of what changes you have, or modifications that you might be able to make. The first one up here is method, and that refers to the directional processing method. For the AWAC, you can either have the maximum likelihood method with the surface tracking or the SUV. So maximum likelihood method is solely for bottom-mounted AWACs, whereas the SUV, you can do this for either bottom-mounted AWACs or for subsurface AWACs that are mounted on subsurface buoys. If you have it actually mounted on a subsurface buoy, you have to use the SUV method. The next one over here is the spectrum, and this is the energy density spectrum, which I am showing up in this plot up here. So you either can use the pressure-based, velocity-based, or the acoustic surface tracking. But what I encourage people to use, end users to use, is to select the optimize, because what that does is it uses the acoustic surface tracking primarily. And if the internal processing deems that the acoustic surface tracking doesn't fulfill the quality requirements, it falls back onto the pressure or the velocity estimates instead. So it's probably always best to use the optimized. Direction. Here you have 4 beams that are checked off, and what this allows you to do is remove a beam from the directional processing. This becomes important if you have a beam that might be hitting, being blocked. So if you have one beam that's not behaving properly because it's hitting the side of something, like a structure, then you can remove it and process with the 3 remaining beams. But please be aware that you always have to have a minimum of 3 beams if you're going to do the directional processing. I'm going to enable it once again. The smoothing allows you to control how sharp these peaks are in the spectrum and how much structure you show in the spectrum. Right now I have relatively high smoothing, which is what I like to process the data with, because it makes it look like the spectrum is similar to what you'd really see. But you can, of course, reduce the smoothing so you have finer resolution. Below this we have the frequency range, and this is effectively the start and stop frequency of the directional processing. So it goes from 0.02 to about a half a hertz, and you see that's what we're showing up here in this plot based on the spectrum range on this axis down at the bottom. And then finally we have offsets. You have the compass offset. So if you, for example, want to report your values in true direction and not magnetic direction, then you can make the corrections according to the magnetic declination from where you are in the world. We have the pressure offset. So if there's small errors in your pressure offset, you can adjust it here. And then finally we have the mounting height. And there's always some mounting height that's non-zero with the AWAC. Typically it's about a half a meter above the bottom, because all frames have some sort of altitude associated with them. So that's all the processing settings that, for the wave processing. So I'm going to click OK. I've made that small change with the smoothing. So if I just step ahead now, you'll notice that this spectrum will show a little bit more structure. So you have a lot more structure in this spectrum. It's typically not what I like, so I'm going to put this back to 64. These numbers are associated with number of FFT bins, for those that are familiar with this type of processing, if you're wondering what those numbers mean. So now that I have selected the processing settings, I can go ahead and process the data. I can either go up to this button under processing, which is start, or I can just start it here with this button. You'll notice that down at the bottom right-hand corner where there's a progress bar, which shows you how long it takes to process this data. It should be done any moment now. And there we have it, all the process data. So now what you have is you have 2 additional tabs down at the bottom. So we have the processed current data associated with this tab and all the processed wave data. What you'll notice is now we have a very similar structure to the windows as before, with 4 sub-windows. Up here we have the wave parameters over the course of the deployment. Below this we have the spectrogram, all the different spectrums that we can select from. And once again we have collections of buttons that are associated with each one of these sub-windows. So I'm showing this spectrogram, which is an indication of the energy distribution throughout the deployment. So on the vertical axis we have frequency. On the horizontal axis, we have the date and time. Other spectrums that are available. One that I actually use most often is called the frequency diagram. And what we do here is for each individual wave burst, we normalize the spectrum from 0 to 1. And this allows us to see a little bit more of the structure or what's going on with the wave climate at any particular given point in time. So if I can use these navigation buttons up here, drop in a line to look at close detail of one of these bursts. So if I pick here, we have low frequency wave event, doesn't have much, that's pretty concentrated at one band. And you can see that up here with the process wave results associated with that. But if I select something a little bit prior to this, you'll see it's a little bit different. You can see that you have more wave energy at the higher frequency and it's overall lower wave energy. I should also state that above this you have standard parameters associated with this particular wave burst and the time. So you have significant wave height, peak period, and the peak direction. Other spectrum that are interesting to look at is the directional spectrum. So again, I click on the button up to the right here in this grouping, and this brings up the distribution of the directions for, again, frequency and deployment. So you get these large areas of light blue, which indicated by this direction bar here. So most of it's coming from about 120 degrees, but then occasionally you get times or periods when the direction's coming more from the south-southwest. You'll notice that data above this particular frequency is not processed, and at this frequency we cannot resolve wave direction unambiguously, so we don't report it. It's a quality control we perform on our wave processing. And the similar is true with our spreading estimates. So we cut off at the same direction, and here we see the structure. Now spreading, for those who aren't familiar with it, it is an indication of what the directional variance is at each given frequency. So you can say when we have wave energy, high wave energy, the waves come more or less with lower, reduced amount of spreading. And when there's low wave energy, they come from a more variety of directions. So I'm going to return this back to the frequency diagram and talk a little bit about what's in this subwindow. This is the parameters, the wave estimates, if you will, the wave heights, periods, and direction. You can see the scaling. Because the instrument was out of the water in the first few days, then you get estimates that are unreasonable. So I'm going to change the scaling. So if I go into scaling, right-click, scaling, I can go in and change the period to something that's a little bit more reasonable. So I'm going to put this from 0 to 10. Okay, and it makes the correct adjustments for the scaling. Okay, if we go to the buttons over to the right-hand side, I'm going to turn off both the period and the direction. Now we just have the wave height. There's a few others here that are a little bit more interesting. I'm going to select what's called the wave count. And this is an indication of how many bad AST detects we had during this particular deployment. So when it was out of the water, we had up to 50%, and that's just meaningless data at this point. And you can't really see any bad detects. But if I zoom in, you'll see that we have some bad detects well below 1%, but you can still see that there are still some points that were despiked in the acoustic surface tracking time series. I'm going to right-click, undo zoom, and now we're back where we were. So I'm going to remove the wave count and show you one more. It's called the wave status. And now what you see with the wave status is how we flag our data for different potential errors. So over on the left-hand side, we have different colors and associated with the different checks. Now, each one of these checks is, or quality controls that we do, is described in our help. And what you see here is that once in a while we have a directional ambiguity. So effectively what we're saying is we detect wave energy at a higher frequency than we can resolve the wave direction. So it's giving you a heads up not to necessarily trust the peak direction at these points where we have these little markers. Okay, so I'm going to reduce this, remove it, and maybe throw back up the direction once again. Let me see, what else did I want to cover here? Yes, exporting function. If you want to include this in reports, it's often more interesting, instead of trying to take a screen dump, is to export what you see in front of you. So I can right-click on this window and I can select Export Data. Here in Export Data, you can select the format which you want it output in. I'm selecting PNG here. I'm going to put it to File and select where I want to write it to. Here I've selected the desktop, and I'll just give it a random name and save. And now it's ready to save to this file. And what you'll find that you want to do is adjust the number of pixels, the size that it comes out at. It defaults to a relatively small size, so I increased it by a factor of 10. Export it, and now it's in a format that's on your desktop, which you can include in reports or whatnot. There is another export function, and you'll find that up in the file, and you can select Export Process Data. What this allows you to do is export all the data that you see in front of you into an ASCII file. So the ASCII file, each one of these groupings of data is exported in individual files in ASCII format, so you can take it into Excel or MATLAB or what you prefer to work with. So you can select any one of these and then export. I'm not going to do it at the moment. You also have the option to export standard estimates, which you would typically find with the AWAC software. I believe this covers an intro to the AWAC, or the Storm software for AWAC data, and I think now it's probably sensible to turn it over to Jan.
We are now open for questions. You can use the raise hand function, which you will find at the top of your screen. Alternatively, you can also type in your questions in the questions from the audience window. So go ahead, guys, if you have any questions, feel free.
I think if we turn back on the Storm software, I'm going to show you something interesting which just popped up to my interest while we wait for questions to come in, because it usually takes time for people to think of questions and to get them off to us. So yeah, while you're thinking, I'm going to show you something on this. What you're seeing here in this particular plot down to the right, this is the full directional distribution. And what's interesting feature that you see here is that you see two energy peaks at the same frequency, but coming from two different directions with two different intensities, which is indicated by the color. Typically, when I see this, it's an indication that the AWAC was close to a reflecting boundary. So that could be close to the shoreline that's reflecting, or a seawall or whatnot. So you have a lot of symmetry in the directional spectrum here. So I think if I step forward, we should see this in several, of the wave bursts. So that's usually an indication of that happening. It probably doesn't happen all the time, but when waves are coming from this particular direction. So what happens when we actually make estimates on this, it becomes a little bit complicated, but it becomes a weighted average of these two peaks. So what becomes reported in this plot up here is a weighted average of these two peaks at that given frequency. So this should be around 100, and that's what you see around here.
Okay, great. Thanks for clearing that up, Torsten. See, we have, as of yet, we have one person, let's see, just trying to get him through here.
Can you hear me now?
Yes, we can.
Yes.
Okay, can you explain us what burst data means in this case?
Okay, burst data, basically when we make wave measurements, it's a little bit different from current profiles. With a current profile, it's relatively short, it's like 60 seconds long, and we make measurements during that period of time and make an average estimate. Now for wave estimates, what we need to do is to make sure that we accurately estimate waves, we have to measure for a long enough time, which we can capture all the randomness in the waves. So this typically is they say it's about 100 wave cycles. So to do that, you usually will have an AWAC or a wave measurement instrument measure for roughly 15 or 20 minutes. So that burst is making a lot of measurements at a high sampling rate for a long length of time. So here we have, I think this is sampling at 2 Hertz acoustic surface tracking for 17 minutes. Is that clear? Mr. Bob?
Yes, yes. Thank you. That's all.
Absolutely.
Okay, thank you. We can move on to the next question that we have. Just 2 seconds. It's from Jessica Skelton. We use the C-State software to process our data in real time, which gives us the option to alter the device mounting height in the setup. Could this give us an offset in the results compared to post-processing in Storm?
Yeah, I mean, if you're going to process in the if you're going to process the wave data in C-State and Storm, then they really should have the same configuration. So if you have a mounting height, for instance, you got to make sure that you have the same, so that they agree. Just so you know, the C-State software is our online software, and it has the same exact processing algorithms for both softwares. So they should agree up effectively exactly the same.
Just looking at the clarification here, she says that C-State doesn't give that option.
Oh, it does it at the time of deployment, that's correct. Yeah, I mean, naturally that would, but it's not going to actually be substantial. It's going to be very minor, and you're only going to see this effectively in any estimates that come from the pressure-based estimates or the velocity-based estimates. So if the AST fails, then it's going to fall back on those. So it's not really going to occur that often. It will happen 1 or 2% of the times, and it'll be a very small error. It shouldn't have, it'll have very little influence on the directional estimates. So effectively, no. For AWACS, this is true. If you're talking about other instruments that are PUV type, then it would be a different story. But for AWACS, they should be very similar.